And hi everybody, thanks for coming. So it's a bit of a dream come true because that's my first scientific book. When I was a kid, I was about 12, and there was Comet Halley that was going through the skies, and it was a big event. And it generated a lot of interest, and many space agencies sent spacecraft, so it was a big deal. And that was one of the big events that pushed my interest for space exploration. And so I wanted to thank Michel and the Keck Institute for Space Studies for allowing this workshop, because the next step is to have future mission to the Comet Halley or to other objects that are once-in-a-lifetime bodies, because I don't think I will be alive when Halley comes back. But so these are once-in-a-lifetime bodies that we want to explore. They are so unique. They bring so much information about the origin of the solar system and the origin of other solar systems. So we are going to work together as part of these studies for understanding how we can make this happen. And so I wanted to introduce my colleagues. So Karen Mitch from Howard University. And Karen is the discoverer of the first interstellar object. Yeah, but I mean, you are the front lead for all the discoveries, and she's a brilliant. She's my friend. She's a brilliant scientist, and everybody knows Karen and her work. And so I wanted to thank Karen for being part of, for accepting to be a co-lead for this study, and then I wanted to thank Sunjo Chung from Caltech and JPL, sorry. And Sunjo is an expert in guidance navigation, and is also at the forefront for developing constellations for complex architecture in order to, what we think will be necessary in order to enable that type of exploration. So I'm going to introduce the first speaker, who is Olivier Hainaut, who comes from Europe. And thanks very much for making that long trip and for being here. And Olivier is on the team of the discovery for Oumuamua, and he's going to talk about the fantastic targets and how to explore them.
So thanks for inviting me. It was kind of a surprise. And actually, I've been working with Karen for the past, 30 years or so. I used to be one of her postdocs last millennial. So the second surprise for me was the title of the talk, which I did not choose. And I'm not a Harry Potter person, so fortunately someone mentioned it to me before the talk. So, okay. So the first question is, what is a once-in-a-lifetime target? And just to get everybody on the same page, we're talking about minor bodies in the solar system on extreme eccentric orbit. So that means that either the orbit is hyperbolic or parabolic, or it is elliptic, but with such a long period that it really does not matter. We will see these objects. They come in, they pass by, they go away, and they're gone. So in terms of origin, what's their story? So let me take you to a history of the solar system, starting with the protoplanetary nebula. This is a profile of the accretion disk as a function of time. And at the beginning, it starts all nice and ordered. All the planetesimal represented by dots are sorted, the rocky ones in red close to the sun, and the icy one that contain volatile ice at a larger heliocentric distance. Then the planets start forming and accreting, and while accreting, they are migrating through the disk, and through that migration, the protoplanetesimals are being reshuffled, and for us, more important, many of them are ejected. So there are various models. This one is I would say, the most realistic, the most advanced, the most convincing one at this stage. It's the Grand TAC and the NIS model. And after all these migration, we end up with a huge fraction of the planetesimals being ejected. Ejected means to interstellar space or parked to the Oort cloud. And so for us, that's really interesting because these objects are so small that once they are taken out of the inner solar system, they are frozen and they are going to be preserved in their pristine conditions for billions of years. So studying them gives us an opportunity to go and dig into the protoplanetary accretion disk. So if they are stored in the Oort cloud, some of them will eventually come back after there is a perturbation. So those that are stored in the Oort cloud will eventually, some of them will eventually come back when they are perturbed by something, a passing star or galactic tide. And those that were ejected into interstellar space are gone. But the hope is that some neighbor stars are doing the same thing, and that we will get the objects that have been ejected by the neighbors. There are also other ways one can kick object into interstellar space. And an interesting one is giant collisions between protoplanets, like the one that form the Earth and the Moon. These collisions are so energetic that a lot of material can be ejected into interstellar space. Other more complex scenario, like a planetary system forming around the binary star, it's possible, it has been observed, it's pretty unstable, and so it's also possible to kick some objects into interstellar space. So this is the situation today, the inner solar system embedded in the Kuiper belt at the center of the Oort cloud. And the Oort cloud is populated by these blue and red icy and rocky planetesimals. So when one of the icy one falls back down to the inner solar system, the volatiles get heated by the sun and they sublimate and form the tail, and that's what we observe as a long period comet. The rocky ones, when they fall down, they are completely or almost completely devoid of volatiles, and so they will appear like a tailless long period comet. So we call them Manx because of these tailless cats. Then the interstellar objects would come also when we are lucky and cross the solar system, and so we call these interstellar objects. So in summary, we have all these fantastic targets, the long period comet, the Manxes, that gives us information on the early solar system, our early solar system, and the interstellar space, interstellar objects that come from other solar systems and could give us some direct information on these other systems. So bottom line, we really want to study them. Now, these, you know, magic comes at a price. These objects are on random orbit. So that means that their inclination will be random. There is no way they will come in the plane of the solar system. And their eccentricity is close to 1 or larger than 1, which is even worse. So just by conservation of energy, kinetic and potential energy being constant, this constant would be 0 for an object on 1 eccentricity. It can be more if the object comes in with an additional velocity. So when they fall into the solar system, potential energy is converted in velocity, and that can be ugly. So an object coming from infinity, arriving at 1 astronomical unit, would have a velocity of 42 kilometers per second. The Earth is at the same distance, 30 kilometers per second. So you already see that the difference of velocity can be 70 kilometers per second if you're not lucky. In the case of 1I, the Oumuamua object, the velocity at perihelion was close to 90 kilometers per second. So That means that we will have to deal with huge delta V's between whichever spacecraft we launch from Earth and the object. Not only huge delta V, but also huge angle between the orbits. So that's the first challenge we will have to deal with, and Hope is going to talk more about that. No, the consequences. So what do we need? What do we want from a space mission? This is just a shopping list. So we want to discover them, we want to know their orbit, their size, their rotation stage, what's their surface in terms of albedo and ideally of composition, what is around the object, is there cometary activity, dust, satellites, why not? And then what's the mass, the density, and the interior structure. So this is a wish list. So first thing is, how do you discover them? That's almost the simplest part. You need a good telescope with a wide field on a beautiful site, a huge camera, and a powerful pipeline. Easy. So these are the two. Okay. Don't press the red button. So these are the two best surveys currently. These are the statistics in purple for Pan-STAR and green for Catalina in terms of discovery of near-Earth objects. And you see that today they discover the huge majority of all the near-Earth objects that are being discovered. And from our perspective, the fantastic targets we are talking about are the same kind of discovery. So how do you discover them? The old-fashioned way is by blinking between images on plates. This is the blink that was used to discover Pluto. Nowadays, with digital images, it works exactly the same way. So here you see a small asteroid crossing the field. It's fantastic. It works beautifully, but you go through graduate students at a very high rate, burning them if you try to do that. So it does not scale well. So the way to do it, of course, is to use computers that try to find all the transient in the images, assemble them in tracklets that make sense in terms of motion. For the good ones that propagate these tracklets to the next night to see if you can get a longer arc, evaluate the results and ask for final confirmation by a human. This is a snapshot of the Pan-STAR pipelines. There are others, but this is really working. So I would say this part of the problem is dealt with. One twist. These two objects are about the same size and about the same distance, but you see that one of them is much easier to find than the other. And so that's a challenge that we have to deal with, but the answer is coming. It's LSST, giant 8-meter wide field telescope with a monster camera that will give, depending which metrics you take, an improvement, a factor of 10 to 100 compared to what we have now. It's coming really soon. 2021 is the official date, but I think they still kind of believe in that date, so it's really coming soon. Next challenge is when we discover these objects. Remember, they come in, they pass, they go away. So this is a statistics of all the long period comets for the past 8 years. This is the perihelion distance in astronomical unit, and this is how long in advance they are being discovered. So you see that most objects are discovered about 6 months before perihelion, which is not bad. Some of them a few years, some of them actually past perihelion. Of course, the latest you discover them, the shortest is your window to observe them. So that's the statistics for 8 years of comets. This is the statistics for all the interstellar objects we have. You see it was discovered just before perihelion. So another challenge. Let me just hammer it down on the case of Oumuamua. Perihelion was in September last year. It was discovered in October 19. And by mid-November, it was getting hard to observe it with normal telescopes. And then pushing really hard, there was one last data point at the beginning of January. So the observation window was extremely short. So that means that once they are discovered, you need to respond extremely quickly. So how to study them? The first question is how fast? And there are various ways to get access to the telescopes. The normal proposal is typically on a yearly or semester cycle. So that means that between the time you ask for the telescope and the time you actually get on sky, you can have between 6 and 18 months, and for various big observatories. So that's available everywhere. That's mostly useless for our purpose. So there are various other ways to speed up the process. Fast turnaround is a rolling deadline where you can get time every 4 to 6 weeks. It's not bad. The best for our purpose would be the pre-approved target of opportunity. You submit a proposal saying, oh, I want to do this, but you don't know the target yet. And so that means that when the target is discovered, you are pre-approved and you can start observing instantly. And instantly means really within the next night. Of course, it works better if there is not a visitor on the telescope on that night. So that works really well for telescopes that operated in Q mode. And finally, director discretionary time. This is the wild card that you can call whenever there is something completely unexpected. Most observatory deals with that quite quickly. It can be actually even faster than 2-3 days. Again, there is the issue of getting visitors out of the telescope. And it also works better if the telescope is multi-instrument, so that you can swap the instrument to whatever you need instantly. So we have had great success. Don't press the red button. We have had great success with the Gemini and the ESO telescopes doing that for Oumuamua. The problem is that you cannot go for the director discretionary time too often. The directors tend to get bored if you come back for the same time of objects. So really the way to go would be to have pre-approved target of opportunities. So what do you want to observe? You can start from the science requirements or from the instrument capabilities. So this is a fleet of instruments at ESO. You know, it's, the same kind of map would exist for any telescope or any instruments. So this is the wavelengths from blue to infrared to mid-infrared, and the resolving power. And each instrument caters a bit of that parameter space. So in an ideal world, you want to cover everything because each of these instruments will cater one of your science case. In real life, however, you have to take into account that your object will put on some restrictions. If it's very bright, you can do everything, no problem. However, if it's faint or fainter or very faint, then you are very limited in what you can do, and you will have to squeeze all the science you can from whatever is feasible. In the worst case, you will be left with imaging in the visible or in the R, because that's where the instruments are the most sensitive. So let me go through the shopping list. How am I doing in terms of time? I have plenty of time. Good. Perfect. So we have discovered the object. Now we want to refine the orbit. Astrometry, that's easy. Just take an image, calibrate it using Gaia stars, and you will get an improvement of the orbit. Just to find the object the next day, a few arc seconds is sufficient. That's super easy. If you want to do more advanced studies on the orbit itself, you need to refine it better. If you want to drive a spacecraft to the target, then you need to be very, very accurate. It can be done using ground-based or space-based telescopes, and that works really well. That's how most astrometry is done. If it's possible, it's really great to get a radar astrometric data point because it locks the orbit with a fantastic precision, but there are some huge constraints in terms of where the object is and what are its characteristics. I mentioned occultation, which is fantastic. It gives you a fantastic precision, but it's horrible to set up. Just look at Mark. He's trying to drive a spacecraft using occultations right now, and yeah. Next parameter that we would like to get is the size. Okay, if you are happy with a rough estimate, it's super easy. You just need to assume an albedo, and you say that if the object is likely a comet or a primitive asteroid, the albedo is 4%. If it's just a normal asteroid, the asteroid is 0.2. And with that, you can convert the magnitude of the object into the radius of the object. And it's really a no-brainer. It works well, but it's based on this assumption that you know what the albedo is, which of course is wrong. If you have enough flux, if the object is bright enough and behaving properly, you can try to observe it in the thermal infrared. And in the visible, you get the reflected light. In the thermal infrared, you get the absorbed light re-emitted as infrared. So you get two equations, flux or magnitude in the visible, flux in the infrared, related to the radius and the albedo, and related to the radius and 1 minus the albedo. You need to throw in a little bit of thermal modeling in there, but at the end you can solve these two equations and get a very good measurement of both the radius and the albedo. Again, the price here is that you need a bright object. Occultations, again, it works beautifully when it works, but it's almost impossible for the kind of objects we are dealing with. Rotation, how is the object behaving? What is its rotational state? Also quite easy, you just need a rotational light curve. Because the object has a changing cross-section as it rotates, it produces variability of the light curve. And the rotational period is then just the period of that light curve. You can also get information of the rotational state. For example, Oumuamua had originally a very nice rotational light curve, but we realized it's actually in a complex state. And you see the light curve is not reproducing itself, so it's not simply rotating, it's also tumbling. Nevertheless, even in case of complex rotation, the range of the light curves gives you some information on the shape of the object. Here we had variations over 2.5 magnitudes, which means it's a change of cross-section of 10. So that means that the elongation of the object is huge, which gave the cigar shape. Careful, you have information only in 2 dimensions of the object. You don't know anything about the 3rd dimension. And actually, in the case of Oumuamua, a 2001 Space Odyssey monolith would give exactly the same light curve. If we want to go deeper into the shape, as I said, a single light curve gives you the elongation. If you manage to get light curves at different stages along the orbit, and the trick is to see the rotation axis under different geometries, then you can invert all these light curves into a 3D model that gives you the 3D shape of the object and also the orientation of the rotation axis. As I said, you need multiple observations over various geometries, which is probably not going to happen for an object that you can observe just for a couple of months, unless you are extremely lucky with the geometry. Occultations. Again, it would be beautiful. This is occultation chords of an asteroid, Cleopatra, and you see clearly the shape of the object. It works for big objects where you know the orbit. For our tiny objects where you don't really know the orbit, it's almost hopeless. Radar can also help. These are radar observations of an asteroid, the BQ6, and actually it looks nicer on screen because you really see the shape of the object, and by doing snapshots at different times you can rebuild the full 3D model. Let's go into more advanced science than just the shape and the rotation. Surface composition. The best would be to have a reflectivity spectrum covering the visible and near infrared, because between 0.5 and 2 micron you get a lot of information. In particular, there is a lot of information in the region between 1 and 1.5 micron. So these are a series of asteroids, and you see that you can really see all kind of information in this region. However, while observing in the visible is easy, observing in the near infrared can be really tricky. So you need a bright object and a big telescope. Otherwise, this just becomes noise. So in most cases, the fallback is to use taxonomic classes. So you just do a few measurements through filters at different wavelengths and try to fit your object into one of these boxes of classes of objects that are well known, and then you say, okay, if it looks like one of these, it must be one of these, and you infer all the characteristics from what you know from that class. In real life, these are two examples. This is C14S3, which is a Manx long period object, so tailless comet. You see the dots, the measurements, and they match really well all the lines which are examples of S-type asteroids. So that means that this Manx is a rocky S-type object coming from the Oort cloud. Here on the right you see the spectrophotometry for Oumuamua, the big dots, and they match really well what you expect from a D-class asteroid. It would be nice, of course, to go further out in the infrared. It was just not possible because the object was too faint. What if the object is cometary active, so sublimating, ejecting gas and dust? If it's very active, it's easy to spot, and I'll come back later on what you can do with that. If the object is faintly active, you can still do things, either because you kind of detect that there is something fuzzy on the image, or if you work with a radial profile. Here you have the radial profile of the object compared to the radial profile of a field star, and the excess is an extremely faint coma that could escape detection. So from that you can get dust production rates and mass loss rates, etc. If the object is really not active, you see here the profiles match all the way to the noise between the object and the reference star, you can still give limits on the dust production rates. And in the case of Oumuamua, we had a fraction of a kilo of dust per second. So even if it's not active, you can go and dig deeper. So this is a heliocentric light curve. So it's the magnitude of the object as a function of heliocentric distance. If the object is just a piece of rock and you plot the corrected magnitude, corrected for the geometry, the magnitude should be a constant. And you see that in the case of this object, the magnitude is all over the place. This is cometary activity, low-level cometary activity on top of the rocky body. You can also play that game with the orbit residual. You plot the residual of the orbit fit as a function of time, and you see that in the case of this object, which is again Oumuamua, there is some systematic residuals that cannot explained just by the gravitational orbit. Putting in a non-gravitational term in the orbit, the residual are completely gone. So r to the minus 2, that's what you would expect from cometary activity. In both cases, you need a fairly long monitoring, either photometric or astrometric. But in the case of Oumuamua, it was possible. So even in the cases that would look desperate, it can be possible. Of course, it would be really nice to see what's inside the object. And that's possible when the object is cometary active. The ice is sublimating, and the sublimation comes from the interior. Okay, maybe not the center, it's just the few top meters, but still you get information on the composition of what's in the object. So the ice is released, the molecules are released from the ice into space, where the UV radiation photodissociated almost immediately. So what you observe are not the mother molecules, these are the photodissociated daughter molecules. And this can be observed in the millimeter wave, in the radio waves, or in the visible. And here is an example for Comet Hale-Bopp, where you can see the whole zoo of molecules that were discovered. Okay, with that resolution, it's not that great, but you see each line corresponds to the evolution of a molecule with heliocentric distance. And just in this paper for this comet, they have almost a dozen different molecules. This was Comet Hale-Bopp, so it's probably the nicest comet of the last century. You can go even one step further and study the isotopic ratio distribution of the object. It's tricky. This is a very short fraction of spectrum in the near ultraviolet. This is the CN molecular band. This is super high resolution. With low resolution spectrograph, all these appear just as one bright line. And you see that if you zoom in on one of these regions, you see the big lines and then all the little lines at the bottom. Most of them are not interesting. You have to focus on those that are marked with little tick marks. And these tiny lines correspond to the different isotopic combination. It's hard. You need a bright comet, you need a super high resolution spectrograph, you need careful data processing, but if you manage to measure the flux ratio between the tiny line and the big one, you get the isotopic ratio, and that has been done for a series of isotopes. And that's of course super interesting because it gives you some cosmogonical information. This is an example just for the deuterium to hydrogen ratio for the Earth and for a series of comets. these measurements are not that easy to obtain. So you see there is maybe a dozen of comets where it has been measured. So what I just shown was done from the ground, either in the visible or in radio. But you see that the spectrum extends on both sides toward the ultraviolet and the infrared. I squeezed the plots so that they are about at the right scale. So that, for example, there is a fantastic line of OH, which is a daughter molecule of water, which is just outside of what we can do. And so it's quite frustrating. It would actually be possible to do it from the ground if the spectrographs would go that far into the UV. It's really at the limit. Similarly to the infrared, there is a lot of information that cannot be obtained from the ground. So space telescopes are needed. If the comet is super active, you can say a lot. You can get a lot of information about the dust distribution. This was started by Finston and Probstein in the 60s. And the idea is you compute the orbit of a dust grain. You solve the orbit for each dust grain, taking into account the ratio between the radiation pressure from the sun and the gravitation from the sun. And you plot the position of each dust grain with respect to the comet and get all kind of information. When Finston and Probstein did it in the old days, it was kind of heroic to compute all these orbits. Nowadays, it's really simple. And so this is an image of a comet, and you can get the intensity of the dust grains depending on their size between 10 to 200 microns. And this works so well. Actually, it's super nifty. You can even run it on the browser on your cell phone, thanks to this Comet toolbox. A guy has produced a tool that works amazingly well. So, yes, good. I'm done. So, going back to my original shopping list of what we would like to know about a target, about one of these fantastic targets. You see the status, discovery, we are okay, orbit, we are okay, size, we are kind of okay if we assume or if we guess the albedo or if we get the thermal infrared, which is difficult. Shape, we are okay if we want just the elongation. If we want the full 3D modeling, it's much harder. Rotation, we are absolutely okay if it's a stable period. To get the orientation of the pole is almost impossible on the short time scale we have. If the rotation is complex, we can detect it, characterize it, but to get a full solution of the complex rotation will probably not going to happen. To measure the albedo, it's the same as the size. It's okay if we can get thermal infrared, which is not easy. Composition, we will always be able to tell you in which taxonomic class the object belongs, but it's really just a first approximation. Otherwise, you need high resolution. You need a higher resolution or spectroscopy or radio to get more detail, but for that you need a bright target. The surroundings of the object, if there is cometary activity, we will get it or we will constrain it, so that's fine. From there we can get information on the dust. Satellites, I did not mention it, but if there is something, we would see it. Mass, forget it. There is no way we are going to get any information on the mass, except if we assume a density and we assume the albedo, which means that it will be really orders of magnitude. And the interior structure, there is really nothing we can do in this short time scale. So in summary, the Manxes, the long period comets, and the interstellar objects we really want to study because they are messengers from early solar systems. And we can discover them, we can study them, all that is fine, but there is a series of challenges. So we need to discover them early, and that is going to imply that we are smart in the way we operate surveys and we detect these objects and flag them as soon as they are discovered. We need to react extremely fast to start characterizing them immediately. If you can observe an object for only 6 weeks, you really do not want to spend 10 days negotiating with observatories to get access to the telescopes. And then be prepared to visit them, and that's why we are here for. And here the big caveat will be to deal with the huge delta V. Thank you.